All righty, let's go ahead and get started. Thanks for coming out tonight. Oh, I do need to remind everybody to silence your phones. So if you would take a second and do that. Greetings, thanks for coming out to hear Dr. Leonard. Before we get started, as always, I have a few announcements. I have a couple of announcements concerning field trips. Due to the government shutdown, our Monday trip to Pinyon Canyon isn't going to happen. Which is a real bummer because this is the third time we've had that trip scheduled, and it's not going to happen. And but I'll keep those who have signed up updated just in case. You never know. But I did send out an email. I think we have a few people in here that signed up for that trip that it more than likely is canceled. For those who signed up for the Sand Creek Big Timbers Museum tour in Lamar, that's on the 29th, and I'm pretty sure the government shutdown should be over by then, and that's still a go. But, yeah. So anyway, there's still some room for that on that field trip too. It's filling up fast, but if you're interested, make sure you email me and I'll get you signed up for that field trip. Also, there's some flyers on this back table with descriptions of that field trip and what we'll be doing and stuff. There'll be no membership meeting in December, but there is a field trip. The Rosemont Museum holiday field trip. Every year, the Rosemont Museum decorates for Christmas, and now is your chance to see the historic house decorated. The December 6th Christmas tour of the museum is not affected by the government shutdown, so reserve that date. There's flyers at the back table, and also Carla has a sign-up sheet back there. And anyway, she is coordinating that field trip. And mark your calendars for Saturday, January 3rd is January 3rd, Saturday, January 3rd from 5 to 7 is our annual holiday party. It's usually on Thursday, but Thursday is the 1st. So this year we had to move it to the 3rd, which is Saturday. As always, the party is a potluck, soup, and desserts with special prizes. Come and have fun with your Paws friends. If you're looking for a good book to read, now that the weather's turning cold and you're stuck inside, the Paws Archaeology Book Discussion Group, next book to read is My Antonia. And My Antonia is a novel published in 1918 by American writer Willa Cather and is considered one of her best works. A little bit about the book. The novel tells the story of an orphan boy from Virginia named Jim Burden and the elder daughter in the family of the Bohemian immigrants, the daughter being Antonia, who are each brought as children to be pioneers in Nebraska towards the end of the 19th century. The first year in a very new place leaves strong impressions on both children, affecting them for life. Our book discussion group meetings are by Zoom. It's not until January 26th at 6:30. So you have plenty of time to get the book, read it, and join us for a lively discussion. And if you've never read Willa Cather, she's really an interesting author. And for one of our book discussion groups, we read one of her books is really good. So consider that. Okay, if we could get Charles and Georgine up here. I have an award to give tonight. At the CAS annual meeting in Denver last month, Paws members Georgine and Charles Booms won a chapter award for outstanding service to Paws and the Colorado Archaeological Society. And I'd like to present them with the awards they won tonight. But before I present them, if you guys want to step over here a little closer, I'm going to tell you a little bit about Charles and Georgine's contributions to Paws and CAS. Georgine and Charles have been members of the Pueblo chapter of CAS since the 1980s. Charles served as president of the Pueblo chapter for several years. Both Georgine and Charles have participated in many CAS and Paws projects including excavations at El Pueblo Archaeological Site with Dr. Bill Buckles. Not only helping to found the Pueblo Heritage Museum, both have volunteered countless hours at the museum. Georgine is the chair of the PAWS display committee that oversees and changes our exhibit here at the museum. And Charles also built many of the PAWS exhibit cases, as well as served as the museum's on the museum's board of directors. Georgine has spent many hours preparing and curating donated materials of the Bill Buckles collection, now housed at the Pueblo City County Library, and has been instrumental in the upkeep of the Nancy and Bill Buckles Archaeological Pavilion at the El Pueblo History Museum. Charles and Georgine have been very dedicated to their work in archaeology and have a sincere belief in science and the legitimacy of PAWS and CAS. This interest has been communicated to the many people that they came in contact with, and they are responsible for recruiting many active PAWS members throughout the years. Join me in honoring Charles and Georgine.
May I say one word?
You certainly can.
I would very much like to say that part of this award should go to Carly Henderson because she's the one who got me into this.
So if you two would hold up your award for the camera for everybody to see who is online tonight. And Georgine, there's your little pin that goes with that. Okay, Georgine and Charles.
Okay, I'd like to just say a word. I was rather shocked when Catherine informed us of this award because I really have not done much here for the last 4 years. Old age didn't just creep up on us, it jumped on us out of the blue and really cut back on what we can do. But thank you very much.
Thank you. Charles and Georgine are very deserving of that award, and they're being modest tonight. Okay, I'd now like to introduce our guest speaker, Dr. Eric Leonard. Dr. Leonard grew up in San Francisco, where during family hiking and camping trips in the Sierra Nevadas, he developed a love of what he later learned were glacially sculpted mountain landscapes. As an undergraduate at Cal Berkeley, he kept up with the trips to the Sierras and majored in history, specializing in history of science and 20th century Europe. After a year spent working as a volunteer at a community center in South Central Los Angeles, he returned to academic study, this time of glaciers and past environmental and climate change. Eric completed a master's degree in geography at Simon Fraser University in Canada, working in the North Cascade Range of Washington, and earned his PhD in geological sciences at the University of Colorado Boulder while working in the Canadian Rocky Mountains. After finishing graduate work in 1981, he joined Colorado College Geology Department, where he taught until he retired in 2019. While at CC, he was a founding member of the Environmental Science Program and for a few years, director of the Southwest Studies Program. Through his time at CC, he has continued work on glaciation and climate history, as well as on tectonics and mountain building throughout Western North America and in Southern South America and Scandinavia. Please welcome Dr. Eric Leonard.
That's not me, just telling you.
Well, here
He gave me notes. Well, thank you, Doug, for that introduction and for inviting a geologist to come down and talk to the Archaeological and Historical Society. I'm hoping that my talk tonight will be of at least some interest from an archaeological point of view. The first part of the talk, I'm going to talk about what Doug was mentioning, the areas in which I've focused my work. Which is that better or is that too loud?
That's good.
Okay, I'm really going to have to yell. The glacial, deglacial history of Colorado and the climate changes that forced that glaciation and deglaciation. So that's what I'm going to. Oh, and that's the work that I've really focused my own research on through the time since I was in graduate school. But at the later part of the talk, I want to move a little bit out of my own field of expertise and maybe a little bit more into some of yours, and talk a bit about the intertwining of the sorts of research that glacial geologists do with archaeological research and the way they can contribute to and challenge one another. As Doug mentioned, I was on the faculty at Colorado College for a good number of years. And through that time, I worked with a slew of Colorado College undergraduates on some of the topics that I'm going to talk about tonight. And I also, oops, I'm supposed to use this little thing for people who are watching online. No, they can't see that. How do I, oh, I remember, I get the pencil thing, right? Does that work? No. Help. I want to get my pointer here. Really managed to mess things up. Thank you.
That's why I'm here, right?
Right.
Got to earn my cookies.
And I also worked with a number of colleagues from other institutions, and I just need to acknowledge them here right at the start. So what are the questions we've been asking and what I want to talk about, at least the first part of this talk? Questions about past glaciation in Colorado, the character of past glaciers, how extensive they were, where they were. Then I want to move on to thinking about particularly the last glaciation. When did it occur? When were there really major large glaciers for the last time in Colorado? When did they disappear? And then going on from that, kind of the why part of it a little bit more. What were conditions like? What were climate conditions like at the time there were major glaciers through the Colorado Rockies? What happened? How did the climate change to eliminate them and to get to the present, essentially ice-free conditions? Then I'm going to move on to what I call musings here, a little bit to talk about how developments in glacial geology and those in archaeology can both inform and challenge the other discipline, how each discipline can help the other one, but also present challenges for the other one. So that's kind of the trajectory of what I'm going to talk about tonight. Okay, so the what and where questions. This is a map that was produced. Can you hear me okay? A map that was produced by the Colorado Geological Survey showing the extent of glaciers in the Colorado mountains at the maximum of the last glaciation. So it's called the last glacial maximum you can see up there. I'll talk about that as the LGM a lot, but that's what I mean. At the time of the last glacial maximum, the kind of significant glaciers in Colorado were of two types. Most of the glaciers, what we would call valley glaciers, those are glaciers which are confined within the topography of a single drainage. They flow from high in the drainage to lower down in the drainage where the snow and ice can melt. And those in Colorado during the last glaciation were anywhere up to 30 kilometers, 20 miles, or a little bit longer than that, the largest ones. There are great examples of them in the Front Range, Northern Front Range, in the Saguache Range here, in the Sangre de Cristos, a little bit smaller in the Sangre de Cristos, even tiny little ones on Pikes Peak during the last glaciation. In a few areas, though, the ice got thick enough and massive enough that it essentially swamped the topography. And so you could get flow across the divides between one drainage and another drainage, and even across the continental divide. And we got what we call mountain ice field complexes. The largest of those covered almost the entirety of the San Juan Mountains during the last glaciation. It was about 5,000 square kilometers, which is about 2,000 square miles of ice cover in the San Juans during the last glaciation. To give you some sense of what we're talking about here, these are some modern analogs. Okay, on the top is the Aletsch Glacier in Switzerland. That's the largest glacier in the Alps today. And it was probably the appearance is very similar to the large valley glaciers in Colorado during the last glaciation, which I should have already said was on the order of 25 to 20,000 years ago. I'll give you more dating later. But so at that time, the big valley glaciers in Colorado probably looked a lot like this. The largest ones were a bit larger than this. Down at the bottom is a mountain ice field complex in the Coast Ranges of British Columbia. It's probably about the appearance, but only about a tenth the size of the complex in the San Juans 20 or 25,000 years. So that was pretty big ice cover there. How do we know that we had this ice cover? Well, there are a whole suite of landforms that geologists would call alpine glacial landforms. They dominate in the Alps, but they also dominate the Colorado Mountains. A lot of features of glacial erosion, these beautiful U-shaped valleys you see all over the Colorado Mountains, very characteristic glacial erosion pattern. These are called cirques, the bowl-shaped depressions you get up at the head of glacial valleys. This isolated peak, the Germans would call it a horn, which form when three or more cirques sort of eat back toward one another and leave an isolated peak in the middle. Again, very characteristic of alpine glaciation. See them all over Colorado. That's Snowmass Peak. This is the east side of Lawrence Peak in Rocky Mountain National Park. And you can see all three of those erosional features, the U-shaped valley, the cirque at the head of the valley, and then the isolated horn. But what I really want to point out in this picture is a glacial depositional feature. Can you see this ridge coming down, dividing the snow from the forest? On the left side of the valley, it actually swings back around down here in the woods and comes back up. Sorry, I'm having a hard time with this cursor. Comes back up on the right side of the valley. That's called a glacial moraine. And the way that forms is the material that was eroded from the top of the valley to form the cirque and the U-shaped valley is then transported by the ice down valley and deposited right at the margin of the glacier. So both along the sides of the glacier, which are the ridges we see, and down at the terminus, the bottom area. So what that moraine is marking essentially is the extent of the ice, the extent of the glacier at the time the moraine was deposited. And that becomes really important for us in the work we're doing because we need to know kind of how big the glaciers were at any given time. So we'll talk a lot about moraines as we go. Okay, so that's kind of the what we're talking about. How about the when? When were these glaciers here? When did they disappear? How can we answer those questions? And probably the first thing would come to mind to an archaeologist, I suspect, certainly comes to mind to a geologist. First thing that would come to mind might be radiocarbon dating. The last glaciation and the deglaciation all fall within the range for which we can use radiocarbon dating, age range of radiocarbon dating. So that would be great. Radiocarbon dating would be perfect for figuring out when this tree was killed, when this boulder was deposited during the formation of a glacial moraine right along the side of a glacier. Alaska would be perfect for that. The problem we have in Colorado and elsewhere in the Rockies is that radiocarbon dating is done on organic material. That's what you have to do it on. There's virtually no organic material associated directly with glacial deposits in Colorado, or really anywhere in the Rocky Mountains. So we can't really use radiocarbon dating. So we've been using another method that developed a little more recently that basically involves measurement of isotopes that are generated by cosmic rays. So let me explain to you what we're doing. Whoops. Oh yeah, well, there we go. It's called cosmogenic radionuclide surface exposure dating. So what the heck is that about? And we're using primarily the isotope beryllium-10. Okay, we have cosmic rays coming in from space, and they don't come from the sun. A lot of people think they do. They're actually coming from somewhere out there in space, and we don't really fully understand where they're coming from, what they ultimately came from. But when they reach the atmosphere, these cosmic ray particles will interact with atomic nuclei in the atmosphere. All sorts of reactions go on in the atmosphere as a result of the impact of these cosmic rays. For our purposes, the most important thing that happens, can you see an N in there? There should be an N in there somewhere.
Yeah.
Oh, okay, it's very faint. Is that high energy neutrons are released by some of these reactions. Okay, those neutrons in turn can interact with surface rock. And again, for our purposes, what we're really concerned about is the interaction of the neutrons with oxygen in the mineral quartz. And you probably know that quartz is a very common mineral in surface rocks. So what happens when the neutron encounters an oxygen atom? Neutron comes in, smashes into the oxygen atom, essentially, and causes what's called a spallation reaction, which creates from the oxygen atom an atom of another element, beryllium, and also several subatomic particles, just the neutrons and protons flying off. And it creates the isotope beryllium-10. Now, beryllium-10 is a radioactive isotope, has a half-life of about 1.5 million years. So for our purposes, that's way more than we need. But what's really cool is that this is the only setting in which beryllium-10 is created on Earth. Okay, there's no other way that beryllium-10 is created on Earth. So we can go to this rock here, one of my students is standing by, and if we measure the amount of beryllium-10 on the upper part, the surface part of that rock, we can use that to calculate how long that rock has been right at the surface of the Earth facing the sky. Okay, and so this is called beryllium-10 surface exposure dating. And that's what we've been using. So a couple of examples of situations where this beryllium-10 dating can be really helpful for dating glaciation. The upper one, that's a moraine that's currently forming. You see the ice right behind it. Stuff's being eroded in the upper part of the valley, transported by the ice down and dumped on the moraine. If the climate changes so the ice front melts back, the moraine is still going to be there. And if some geologist comes along in a few thousand years, they can go to each of these boulders and sample the top part of the boulder, measure the amount of beryllium-10 in it, and tell you how long ago that boulder was deposited there on the moraine, so therefore how old the moraine was. I should say that the neutrons don't penetrate very far into the rock. So most of the beryllium-10 is right very close to the surface of the rock. Okay, so here are just a couple of examples of sampling we've done now in southern Wyoming. On the left is a large boulder on a moraine with the last glacial maximum. The moraine is now, it's thousands of years old, so it's got trees on it and everything. But we can sample the top of that. We did sample the top of that and get an age for the formation of that moraine. You have to get multiple ages to be sure you don't have any errors going on. On the right is a glacially eroded bedrock outcrop in the same valley, but several miles up valley. In the lower right, maybe you can see that's the rock, and it's striated, scraped along parallel to the pencil there. That was by ice or material being carried in the ice. So we sampled the top of that, got a beryllium-10 age on it, and that told us when the ice front retreated, melted back past that spot on the way up the valley. So using these two, we can kind of get at both the timing of the maximum stand of the glacier and also the history of retreat of the glacier. And that's what we've been doing as far as chronologies. And I'll show you an example. I love this upper frame. That's a sketch from the Hayden survey 151 years ago of beautiful set of glacial moraines around Twin Lakes in the Saguache Range. You probably know this area. To the left here, you'd go toward Buena Vista. To the right, up toward Leadville. The road to Aspen goes along the right side of the Twin Lakes and goes back across the Continental Divide at Independence Pass. The lower frame is a photo that we took from a small plane a few years ago, looking up into the same area. Interestingly, the moraines show up better in the Hayden survey sketch than they show up in the photograph. So in the lower one, we've labeled those moraines LGM moraines, last glacial maximum. That's what we thought when we took the photo. Turns out to be only partly true, which I'll get to in a minute. So sometime after, and I haven't said, well, I called them LGM, but sometime after the ice was out to those main moraines, the climate change, the ice front melted back some distance, but then restabilized for a while and deposited another moraine. It's called a recessional moraine. It's during the recession of the ice front. The recessional moraine is actually the ridge that makes the Twin Lakes, cuts them in half. Okay. I guess I don't need this. That research team was to remind me of what I was going to say at this point, but I remembered. I worked in this area with 2 Colorado college students and some graduate students and faculty from universities of New Hampshire and Buffalo. We worked in this valley on the moraines, trying to date the moraines, and then also on the glacially eroded bedrock all the way back up. Oh, I should say the glacier that came down this valley was about 30 kilometers, 20 miles long. So we worked all the way back up there, trying to get a sense of the timing of the last glacial maximum and then the timing of the recession. We did it in this valley and the next 2 valleys to the south. What we did, so this is what's called the digital terrain model of the area right around the lower Twin Lake. So north is up there. You can see the moraines in here. You can see the recessional moraine back here. The ages on there are all beryllium-10 surface exposure ages on boulders. I don't know why we got so many. Somebody had a lot of ground. The ages are expressed in thousands of years before present. And BP is what geologists talk about. I think archaeologists talk about BC more than BP. So if you want to change these to BC, subtract about 2,000 years. Is that right? Yeah. But anyhow, these are years, thousands of years before present. If you look closely down here on the outermost moraine, there are a bunch of ages of about 130,000. Okay, that's not the last glaciation. That's the glaciation before last. So the outermost moraine was actually deposited during the glaciation before last. But as soon as you go inside there, there's a slew of ages between about 21 and 23,000 years. And those mark the maximum stand of the glacier during the last glaciation. When you go back to the mid-lake moraines, you've got a bunch of ages about 6,000 years younger, about 16,000. So ice was out here 22,000 years, more or less, ago, out in this whole area. But the ice front had retreated back by 16,000-ish, right back to here. Okay, but we still have 25-kilometer long glacier. When did we get rid of that? We don't have any moraines, but we've got lots of glacially scoured bedrock up valley. So we went up valley sampling outcrops like this. Our valley here was the northern one. Didn't put the age of 22,000-ish out there. Here's the mid-lake moraine around 16,000. Takes it 6,000 years to get back there, but it takes only another 2,000 years to get all the way up to the end of the valley. So by about 14,000, ice is almost completely gone. Tiny little bit up at the head of the valley. But it's basically gone in that 2,000 years. And the other two valleys to the south, probably a little hard to read, but have essentially say the same thing. Ice is there in the, at the end, I'll summarize in a second. Because we've done this, we and other groups have done it in other valleys around the state, and we see a very similar overall pattern. So glaciers reach their maximum extent 20 to 23 or 24,000 years ago. They stay big. They retreat back a little, but they stay big until about 16,000, and then they retreat really fast and disappear really fast. So something's happening between about 16 and 14. And by about 14,000, all or nearly all the ice is gone from most mountain ranges in Colorado. A little bit of ice hangs around for a few thousand years in sheltered areas, maybe coming and going as the climate varies a little. I know you guys use terminology, but in the latest part of the Pleistocene going into the Holocene, which begins about 12,000 years ago. But by 10,000 years or so ago, everything's gone. And there are modern glaciers in the Northern Front Range, some tiny little ones in Rocky Mountain Park and in the Indian Peaks, but we're pretty sure that those disappeared entirely through the middle part of the Holocene and came back just in the last few thousand years. Things got a little colder. Okay, so that's the chronology for this area, but a general chronology kind of in the Colorado Rockies of glaciers. What does that tell us about climate, or what can we infer about climate from that? How much colder or snowier or both was the climate 20,000 years, 22,000 years ago when the glaciers were at their maximum? How much warming or drying or whatever did we need to get rid of those glaciers pretty rapidly, particularly after about 16,000 years ago? To look at those questions, we've been using, I see both this figure and the next figure on the screen here. And so I suddenly look at that next figure, so I'm not ready to talk about that yet. So we've been using a numerical glacier model that essentially what it does is it grows the glacier that would form in a particular topographic environment, i.e. that big valley above Twin Lakes, the glacier that would grow there under a climate that we input. So we're obviously, if we did it with a minor climate, we wouldn't grow a glacier. But we begin with sort of a hypothetical climate. We say, well, if it's 5 degrees colder, what kind of glacier would grow there? How big would it get? Where would it stop growing? And we're trying to make it grow exactly until it reaches the moraine and stop growing at that point. Okay. And so, but what of course happens the first few times is the hypothetical climate you put in, say twice as much precipitation as today and 5 degrees colder. I don't know. Put something in like that. And if the glacier grows, remember this valley is 30 kilometers long, but if it stops somewhere on the way down, we know we haven't made it cold enough or wet enough or something. We have to go back, rerun it, run the model several times until we get a good fit. Sometimes it overshoots and made it too cold. Okay, so let me just show you an example, and I'm not going to show you a model run of this glacier. It's a big glacier. The model takes a long time to run. I want to go down to a much smaller glacier in the Sangre de Cristos, right behind the town of Crestone. People may have gone up the Willow Creek Valley. It's a beautiful valley there. Anyhow, during the last glaciation, ice came out of a cirque here, floated about 6 kilometers down, and I think you can see the moraines of the last glacial maximum down there. So what we want to know is what we have to do to modern climate to grow a glacier that will flow down just to those moraines and stop at that point. And this model run I'm going to show you, I can tell you it wasn't the first one we ran. What we did is we depressed temperature 5 degrees Celsius, which is 9 degrees Fahrenheit, left precipitation just the way it is today, and looked at what glacier would grow under those conditions. Just gonna, it worked before, but it's not working.
There's no glacier at all.
There's no glacier at all. Do you know why I can't get my thing to come? Oh, there it is. There it is. Okay, I was gonna tell you a little bit before that. Okay. Well, you've seen it. There's the punchline. It takes about 200 model years for the glacier to stop growing. It stops growing when it's equilibrated with the climate, right? So in this case, this was not the first one we ran. We ran some that overshot and some that undershot. But finally, when we got to about 5 degrees temperature depression Celsius, our glacier grew right almost, it's a tiny bit short of the moraines, but if I made this 5.1 or 5.2 degrees, it would spill over and go down into the valley on both sides. So we're pretty happy with that reconstruction. We also modeled the next valley to the north. Here are a couple of cirques that contributed to that glacier. There's one more, I think, out of the view. Here's a moraine. When we did that, we came up with almost identical best fit. I think it was 5.1 degrees Celsius. So we're pretty happy with that. We've done that in several ranges across the state, and actually down into New Mexico and up into Wyoming and even Montana. Here are the results we get in Colorado. This is the area we were just looking at, about 5 degrees temperature depression. It differs place to place, but it's actually a pretty tight cluster from 5, which is 9 degrees Fahrenheit, to about 6.5, which is 11.5 to 12 degrees Fahrenheit temperature depression if we don't change precipitation. Okay, 5.4, that's what we got at Twin Lakes. So I'm going to return to Twin Lakes in a second, because the next question is, how much did we have to raise that temperature, and kind of how fast was it rising to deglaciate the valley? So we go back up to Twin Lakes. Twin Lakes Glacier is the northern one here. Here at the last glacial maximum, about 22,000, it's 5.4 degrees colder. 6,000 years later, ice has retreated about 5 or 6 kilometers up to the mid-lake moraine. It takes only about 0.5 degree Celsius, just under 1 degree Fahrenheit, to make it retreat that far. And that's a very slow warming over 6,000 years. The rate kicks up after that, and in about 2,000 years after that, the ice is way back up here. It takes a little more than 2.5 degrees warming in that 2,000 years, which is about 4.5 degrees Fahrenheit in that 2,000 years between about 16 and 14,000 years ago, to get the ice way back. So they're just tiny little bits of it. And then actually to get to modern conditions, we need another 2.5 degrees of warming beyond there to get well, to conditions where we need to drop temperature a couple of degrees to see any ice in there now. Okay, one of the things to take away from this, and maybe it's a little bit sobering, if you think about it, this glacier was about 30 kilometers long. It took a total of about 3 degrees Celsius or 4.5 degrees Fahrenheit warming to get rid of a glacier of that scale. And so when we're talking about contemporary warming and trying to limit it to 1.5 to 2 degrees Celsius, that doesn't sound like very much. But if you look at a system like this, 1.5 to 2 degrees Celsius has a huge effect on this system. Okay. Now, nobody's in the back raising their hand and saying, hey, but you keep saying, assuming there's no change in precipitation. All these models have said that. And is that a good assumption to make?
No.
Almost certainly not. So how can we deal with that? I mean, we can't deal with every aspect of it, but I'll show you what we've been trying to do. Okay, we have a 2-variable problem, and that's an understatement. We have a multivariable problem. That multiple variables control the glacier, the real glacier, and they also control our model glacier. And all we've been doing is tweaking temperature. It turns out when we run what's called sensitivity analysis, you run the model and you change one variable at a time and see how that affects things. There are 2 variables that are really centrally important. And one is temperature, and it's really the temperature during the summer melt season is the critical temperature. And the other one is precipitation. We say winter precipitation, but it's really precipitation from fall through spring, anytime that precipitation can fall as snow. And those 2 between them are the real controls. And clouds and windiness and stuff like that exert an influence, but it's distinctly secondary or even tertiary behind the big temperature precip control. So what we do is run models with multiple precipitation inputs to see what they look like. So this is, again, back at Twin Lakes. And here are just 4 models we ran. This is precipitation relative to present. So the number 1 means the same precipitation as present. It takes 5.4 degrees to generate that glacier. If we have precipitation, it takes about something like 7.6, 7.7 Celsius to get a glacier of that size. If we increase precipitation by 50%, it's only 4 degrees, and you could be anywhere along that line and get a glacier that would work. And unfortunately, our model can't really distinguish between those, which can be frustrating. But let me show you some things that we can do, even not being able to distinguish. So I plotted 4 results from 4 glaciers here, 2 in northern New Mexico, Santa Fe Range, the southernmost part of the Sangre de Cristos, down by Santa Fe on the left, and then in the Medicine Bow Range in southern Wyoming on the right. I didn't put the Colorado ones on here, but they look like the Medicine Bows, basically, and not like New Mexico. So what is this telling us? Okay, the x-axis here is how much temperature was depressed. The y-axis is what happens to precipitation, right? And what this seems to be telling us is that the LGM, the glacial climate in New Mexico, was more different from the modern climate in New Mexico than the glacial climate in Wyoming was from the modern climate in Wyoming. So the climate change between the last glaciation and now was more extreme in New Mexico than in Wyoming. And the easiest way maybe to interpret this would be to say, well, temperatures got a lot colder in New Mexico compared to today. Temperatures were 8 or 9 degrees colder than today in New Mexico 20,000 years ago. And in Wyoming, they were only 6 degrees colder than today. Turns out that's very unlikely if you have any belief in climate models. Every climate model that I've ever seen modeling the climate of the last glaciation says in the Rocky Mountains, temperatures were depressed more in the north, close to the big Canadian ice sheets, and depressed progressively less south, as you get away from the ice sheets. So these things maybe ought to be flicked. But the climate models also say, virtually every one of the last glacial maximum, that precipitation was significantly less than modern in the Pacific Northwest and in the Northern Rockies, and significantly more than modern in the Southwest and the Southern Rockies. So my interpretation of this is most likely we're looking maybe in New Mexico, in through Colorado and Wyoming, relatively uniform amounts of temperature depression. It was 7 or 8 degrees colder than the present, but those cold temperatures were accompanied by very dry conditions, significantly drier than present in Wyoming and into Colorado, significantly wetter than present, at least in the winter, in New Mexico, which finally might be leading us to something of a little bit of interest to folks in this room with their more specific archaeological interests. There's now, and you guys may disagree with this and we can talk about it, and I will talk about it in the next little bit, but there's now what I think is a fairly compelling evidence that there were people in southern New Mexico, at least at the time of the last glacial maximum. And this kind of work, the climate models, and I should say other types of what are called proxy records of climate, lake levels, vegetation records, isotopes, all suggest these wet conditions, winter wet conditions in the Southwest. And so conceivably, what we're talking about, well, I think probably what we're talking about, if there really were people there then, was they were living in an environment that was both quite a bit colder than present, but also quite a bit wetter in the winter. So quite a bit more water availability at that point than in the present. Okay, well, that leads me really to my final topic, where I get on shaky ground here. Maybe I was already on shaky ground. I got an even shakier ground. Talking about how glacial geology and archaeology can really interact and have really interacted, and how each discipline can help answer some questions in the other discipline, can also provide challenges for the other discipline, force people in the other discipline to go back to the drawing board. And so that's what I want to talk about for a little. I first became aware of kind of the potential contributions between the two fields when I was a graduate student in Boulder. And I became aware of work that was being done by a guy named Jim Benedict. I don't know if you know that name, in the Front Range at the time. What Jim did basically is he was both a glacial geologist and an archaeologist, and he worked on developing a very detailed record of small scale, really, glacier variations from about 12,000 years up to the present. And from that, sort of made inferences about how climate was really influencing patterns and timing of human occupation, human utilization of resources in the Front Range at middle to high altitudes in the Front Range. And he did the archaeological work also. So I'm sure that the glacial work, now this was 3 decades ago, could be redone now and improved. His work was good, but we have new methods now, beryllium 10, for example. I suspect the same thing's true of his archaeological work. I don't know what archaeologists think of him these days, but he really impressed me at the time, the way he could use the two disciplines to complement one another. And I think there are many other examples of that. And I just want to finish up by looking at one more example on a regional scale. It's a much bigger example. It might be maybe the best example there is about the interaction between the two disciplines anywhere. And that's a question which I'm sure you are all somewhat familiar with, is the whole question of when and how people arrived in North America, south of Beringia and south of the big ice sheets. Okay. And this to me is a perfect example of interaction of geological and archaeological research. So again, this probably isn't news to you guys that through most of the 20th century, kind of the dominant model, dominant answer to that question, somehow, well, it's the answer to the question, but the accepted constraint on human arrival south of Beringia was sort of the Clovis first model, that the first solid indications of people south of the ice sheets was during time of Clovis culture, 13.5 to about 13,000 years ago. There were always people who disagreed. And about 25 years ago, the Monteverde site in southern Chile became pretty well accepted, I think, as indicating that there were people in southern South America at least 14,500 years ago. So that kind of changed the ground a little. But we also have known for a long, long time that at the last glacial maximum around 21,000 years ago, this humongous Laurentide ice sheet that covered virtually all of Canada east of the Rocky Mountains was confluent with a smaller but still huge Cordilleran ice sheet that covered virtually all of Canada west of the Rockies. The two were joined over quite a distance. And there's a saddle that we now think was about 2 kilometers thick, at least at the last glacial maximum, that most people think precluded the possibility of people getting through between the two by an inland route while that ice was there and while they were confluent. We know a lot less about how much ice there was the last glacial maximum on the West Coast. I think most people have agreed that at the time of the last glacial maximum, there was too much ice for people to get down by a coastal route. So the big questions over the last several decades have been, when did these two routes open? The ice-free corridor between the two ice sheets in the middle, or when could people get down along the coast? And how do those times compare to the time when we think there were people for south of the ice sheets? And trying to answer this, obviously the archaeologists are very involved in this question, but also the geologists have been throwing their whole toolbox about, reconstructing glacial history and glacier positions, and also for the coastal route, reconstructing sea level history and patterns, which is a really big issue for that route. And just real quickly here, a couple of fairly recent studies, one along the coastal route of when lands became exposed and above sea level, when they became deglaciated. Here's the interior route, without looking at any of the details there, or any of their myriad studies. I think it's safe to say that in the last decade or so, it seems to have become clear that significant portions of the coast were ice-free and above sea level by about 3,000 years before the ice-free corridor really fully opened between the two ice sheets further in. And that has kind of led people, but again, you guys may disagree, led people toward the coastal route. But so that's where we were 5 years ago. And about 5 years ago, and again, this probably isn't news to you, some interesting information came out of White Sands in New Mexico. Footprints were discovered, and in 2021, a paper was published with ages of those footprints, at least purporting to be the ages on the footprints. And they ranged from 23 to 21,000 years ago, which is right at the peak of the last glaciation. And there was initially a lot of controversy about those ages. How good were they, and were they really dating what they're trying to date, and so on. Subsequently, 2 more papers have come out, one 2 years ago, one earlier this year, independently dating, some of them using different methods, using different samples, and coming up with essentially the same answer. So suddenly now archaeologists throw, if we believe this, a big question back at the geologists. Okay, how do you get people down here by the last glacial maximum? And then the question actually becomes a harder question. The question we've been trying to answer was before White Sands was, when did these routes open up after the last glaciation that would let people get down? Now the question maybe is, when did they close before the last glacial maximum? What was the last time people could have gotten down? That's a much harder to answer question for the geologists, because glaciers basically, advancing glaciers basically erase their own record. As they move over the area, they erode away moraines, they pick up the boulders and organic material that we would have used for dating where they were, and they just move all that stuff out of the way. And so it's very hard to reconstruct the advance of ice. It's much easier to reconstruct the retreat of the ice margin. And so it's a much harder question. And frankly, I don't think I'll go through these at the moment, because I think I'm over in time. If anyone wants, I can go through them later. But basically, okay, I'll just tell you, this is the most recent compilation we have of the advance of the ice sheets from 35,000 to 30,000, from 35,000, I'm supposed to point this out, to 30,000 to 25,000. But if you look closely at this, there's a whole bunch of uncertainty there. Minimum estimates, maximum estimates, best estimates. I think at this point, we don't know. And I'm not criticizing this paper. I don't believe anything in this paper, but I'm not criticizing it. They're using all the data we have available. And they're using it very well. And they're estimating, well, here's our best guess, and here's the maximum it could be, here's the minimum it could be. That's all good work, but it's not giving us an answer. So I think this is an instance where maybe geology ultimately will give some good answers to archaeology, but archaeology has now presented a problem to geology that we can't solve yet, and we may need to develop some new methods to solve. So I think I'll leave it at that. I've probably gone over a bit. So I want to thank you very much for the invitation and putting up with maybe a little more of the geology than you bargained for. And I want to thank the folks who funded us for this work along the way. Yeah, and I'm happy to try to answer any questions.
I'm having trouble with the temporary test field or lab process.
Both. I mean, the test is lab, but I'm sorry, is the 10 beryllium analysis, is that a field process or a lab process? And it's both. You have to go out and sample the rock in the field, and that can be a real pain because you're trying to get the top 1 or 2 centimeters of rock off the top of a boulder. And if you're working in a wilderness area, you can't use anything, electric or gas powered or anything. You have to go out there with a hammer and chisel. But the separation analysis is done in the lab.
Another question. How did the younger Dryas affect the Rockies?
Oh, how did the younger Dryas affect the Rockies? That's a good question and a debated question. Okay, the younger Dryas is during the deglaciation that happens from, begins about 20,000 years ago and is completed maybe by 10,000 years ago on a global scale, a little after. So it's generally warming, but there's a short interval that the onset is very rapid and the end of it is very rapid of cooling. And the total cooling, at least around the North Atlantic during the younger Dryas, that's called the younger Dryas period, is about half of the total warming that goes on during the deglaciation. Temperatures go up, 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 boom, down, stay down for about 1,000 years, come back up really fast. And that's the Younger Dryas. How it affects the Rockies, there's a lot of debate about that. In Colorado, nearly all the glaciers, maybe all the glaciers, were gone by then. And so there's very little direct evidence of glaciers re-advancing during the Younger Dryas. In Colorado, I've been involved in some discussions of whether there's evidence in the Canadian Rockies where I've worked. Some people think there is. Some people think those moraines that are proposed to be Younger Dryas re-advance are actually of other ages. It's very clear this is a major event around the North Atlantic Ocean. The glaciers, that were retreating in Eastern Canada, in Greenland, in Norway, in the Alps, were retreating back. They re-advance and then retreat again 1,000 years later. It's less clear globally than that. So is it just a North Atlantic event related to circulation in the ocean in the North Atlantic? Or is it truly a global event? I don't think I don't know. I say we don't see evidence of it really in Colorado, but it may be because all the glaciers are gone. So I know I didn't answer that question.
I think the footprints, these footprints here, could they have came in from South America versus open land route?
So the question is, could the white sands footprints indicate people coming from South America rather than over the land bridge? I'm going to send that one back to you guys. I think that's more a question for archaeologists than for geologists. I don't think there's the Darien Gap and all sorts of stuff, but there aren't any major impediments like ice sheets between Monteverde and White Sands. But I don't know. That's way out. Yeah.
The question I have is, was there ever elevation to brought into this because you can see in Colorado, so the mountains grew in 600 years ago to way higher levels. So was that also in these models, maybe partially because they were a couple thousand feet higher at one time?
Yeah, the modeling we're doing is over the last 25,000 years or so, and the amount of uplift or downlift subsidence is pretty minor over that time period. One thing that may go on, because I did some modeling trying to do the 130,000-year-old glaciers versus the 25,000-year-old. Even in that time period, there's not much uplift, but somebody pointed out, yeah, but the glaciers 130,000 eroded the valleys, and so the valleys were actually deeper by 25,000 years ago. So that might have been going on. But I think in terms of what we call tectonics, overall uplift of the mountains, our time scale is way too short.
You mentioned that you were kind of tree stuff in not in Colorado. Why? What's the difference?
Well, I think there are a couple of differences. The glaciers, well, if you look at modern glaciers, okay, glaciers come down below tree line in Alaska, right? And so they knock over trees. In fact, that was a very young, that picture I showed was only a couple of 100-year-old tree. Probably wouldn't have been that good for radiocarbon, that got knocked over by an advancing glacier. And that happens in Washington State and places like that. It doesn't happen with modern glaciers in Montana, although as you go north into Alberta, Canada, the recent glaciers did come down and knock over trees. It's dry here, and was dry in the past, so there are a lot of trees, tree line, least the lower tree line is very high. I don't know actually that there were significant trees at all in Colorado. I'm getting again out of my field of expertise, but during the last glaciation, upper tree line comes down. I don't know where the lower tree line went then. But basically, a combination, I think, of the aridity compared to Alaska, and I guess it's probably aridity that drives the whole thing. So the glaciers, certainly the modern glaciers, come way below tree line there, and they don't here.
Same question. On the beryllium moving down outer space,
Right.
it's building up layers on the rock. And so you're measuring the thickness to get the age, correct?
No, it's not actually a thickness. What?
You have to be measuring something.
Well,
because this deposition is occurring over time to give you a time.
well, the neutrons come in, and impact the mineral. Okay, smash into the oxygen in the mineral and cause that oxygen to change to beryllium. But there are also neutrons and protons given off in that reaction. So I'm not sure what actually happens to the mass of the mineral.
Well, you have
state.
to have something to get the age. So
Oh, well, the age is then what you what you do is you I'm not the one who does the lab work, but basically you take the quartz, you extract the quartz, and you look at how much beryllium 10 there is. Oh, man.
So it's a
Relative to what? Maybe relative to the mass of the quartz or the total or the amount of oxygen. I can't remember the detail, but you're basically looking at the proportion of oxygen that has been converted to beryllium.
For that to work over the 10,000, 20,000, 30,000 time frame, the cosmic rays coming down have to be uniform the whole time frame.
You got it.
So it's very, very.
There is, and there's a lot of modeling of that. The real time variability is a good question. There is time variability, I'm sure, because the cosmic ray influx into the upper atmosphere is also what creates carbon-14 that's used in radiocarbon dating in the upper atmosphere. And we know the rate of carbon-14 production changes through time because the cosmic ray influx changes through time. And that's how we get calibrated radiocarbon dates that try to take that into consideration. I believe, I'm not the one who does the beryllium dating, I do the sampling, but I believe that they also do that. There's a whole bunch of work on what are called production rates. And I think there's a time variation in the production rate, what you're alluding to. You also need, in that case, to worry about altitude and latitude, because those things influence, well, initially the latitude influences where the cosmic rays go, Earth's magnetic field, and the altitude influences how many of those neutrons actually don't make it through, or do make it through the atmosphere. So that,
volcanoes erupting. And there's been research papers when they've done core samples into lakes, the Great Lakes, for example, to see all the temperature variation, pollen and all that stuff.
Yeah.
So that's a different field, actually. But it's
Yeah.
a crossover with glaciation.
oh yeah, I mean, there's a lot of crossover between people who work, paleobotany or something, things like that. Vegetation change. I worked with lake cores through my PhD. I wasn't looking at that. I was just looking at the sediment pouring out of the glaciers, trying to understand that. But other people were looking at cores from the same lakes, at the vegetation changes, and there are all sorts of isotopic things that you can read. And they all tell a pretty similar story, although they have different sensitivities to different aspects of climate.
Sure. Starts for 2.6 years ago.
Right.
To the higher.
Mhm.
And you have the Rocky Mountains over here, I think. You know, 175 billion or less.
Yeah. So the question that we have the ice ages that begin about 2.6 million years ago and continue, probably still continuing, but the last glaciation ended about 10,000 years ago. The Rockies were here, as you say, they formed, the modern Rockies probably began forming about 70, 75 million. Well, there's a lot of debate at what do you call the modern Rockies, but they're certainly 2.5 million years ago, there were big mountain ranges here. 2.5 million years ago, they might have been lower and a little higher. 25,000 years ago, they were basically
Kansas. And in the very east section, there was influence by glaciers.
Yeah.
I remember my father realized finding years later I found some hills in the northeast part they're covered with these huge granites. I mean,
really, yeah, from Minnesota or Canada. Yeah. So the question was about. I'm supposed to do this for the people online. The observation was that in northeastern Kansas, there's evidence of glaciation in large boulders that probably came down from Minnesota or maybe from Canada. That's when I was talking about the two big ice sheets, the Laurentide being the really humongous one. It came down multiple times out of Canada. The last time it got down about as far as the Missouri and Ohio rivers, maybe a little less than that. But at times it probably got down as far as Kansas. So that's a big continental glacier. I've been talking about alpine glaciers, mountain glaciers. But yeah, I mean, those are much, much bigger and have very rich history too. And do a lot more things. Not only are they results of climate, they very strongly influence the climate in a way that our little glaciers don't.
Do they get to use the same tools or the same testing procedures for glaciers in Kansas and Minnesota we're using Colorado? Are they going to use measuring the same thing just in a different location, or do they have to their own tools to do it? I'm using the word tools.
Yeah.
Sure.
Yeah. So the question is about tools that are available for looking at big continental glaciers versus what I was talking about for alpine glaciers. I think they're mostly the same. Certainly the dating tools are very, very similar. Let's see, well, I was going to say something about obviously the scales are different, but what was that I was thinking of? Oh yeah, so the modeling. I mean, I was talking about modeling these little glaciers in Colorado, 10 miles long. There's a ton of modeling going on the big ice sheets. It's way more complex because they're just geometrically huge and complex. But on the other hand, our models, we use the grid size of our model is like, I can't remember, 10-meter grids, I think. So we're doing calculations every 10 meters. They're using 5 kilometers or something like that to model Greenland because they can't, because even though their computers are way bigger than our computers, the process, because those are so huge. But the tools, I think, are basically the same.
Well, thank you.
Yeah, thank you.
Thanks everybody for coming.